What is the variability of soil? Soils change throughout time in fields and between farms. Uneven litter decay, soil moisture content, vegetation composition, topographic position, land use pattern, and soil management technique can all contribute to soil spatial variability. In different peat lands, these factors may have a distinct impact on chemical and biological processes. What is the sensitivity of soil? The sensitivity of soil is defined as the ratio of the unconfined compression strength of clay in the natural or undisturbed condition to that in the remolded state, without any change in water content. The strength of soil can be higher in its unbroken state than in its remolded state. This category includes a lot of cohesive soils. Soil sensitivity is the ratio of shear strength in the uninterrupted condition to that in the entirely remolded state, and it describes this behavior. A decrease in intensity is frequently noticed when the strength of an unmoved piece of clay is assessed and then determined again after reshaping to the same dry density at the same water content. This is a serious occurrence that has the potential to cause harm and is measured with the formula below. Say equals SU, undisturbed, /SU, remolded. Coarse-grained soil. Individual grains that pass through a number 200, 0.075 mm, sieve are described as coarse-grained soils. The smallest grains may usually be seen with the naked eye, though a handheld magnifying glass may be required to see the tiniest grains. Gravel and sand are soils with a coarse grain. Normally consolidated soil. This situation is described as normally consolidated when the first vertical effective stress is approximately equivalent to the pre-consolidation stress. To prevent misclassifying soil, we'll assume it's generally consolidated if the initial vertical effective stress and pre-consolidation stress are around 20% of one another. Over-consolidated soil. Over-consolidation is a relative phrase that compares the stress acting on the soil in its current state to the soil's greatest stress level. If the current stress is less than that previously applied, the soil is already over-consolidated, and vice versa. Residual deposit soil. A residual deposit is one that has formed due to the alteration of an existing rock that has lost a considerable portion of its contents due to dissolution and has thus become enriched in specific minerals or other elements. Bauxite, for example, is an aluminium ore generated through the modification of several types of rock containing aluminium elements. Organic deposit soil. When temperature or pressure is lowered, heavy hydrocarbons precipitate, causing damage. These deposits are frequently found in tubing, gravel packs, and perforations, as well as inside the formation. The use of cold treatment fluids encourages the growth of organic deposits. Aromatic organic solvents like toluene or xylene resolubilize organic deposits like paraffin or asphaltenes. Normalizing versus for field assessments. The observed versus of deeper layers would be expected to be greater than those of shallow layers even when the site has homogeneous density, as the mean effective stress increases with increasing depth in natural soil deposits. The effect of confinement, or overburden stress, must be taken into account when assessing the density of a material based on in situ versus normalization with depth or overburden pressure has long been acknowledged in various investigations, particularly those for SPT, Standard Penetration Test, and CPT. When the in situ vertical stress is 100 kPa, Pa, the normalization was meant to provide a benchmark value for the shear wave velocity at a specific depth, typically the depth equivalent to an overburden pressure equal to an atmospheric pressure of 100 kPa, Pa. Because versus takes null values if the mean effective stress is zero, this aspect presents significant challenges if surface conditions are to be considered. This limitation necessitated the adoption of an alternate normalizing strategy that incorporates the midway condition of a specific seismic stratigraphic layer, as indicated. A layer's midpoint pressure becomes the standard for normalization, therefore VSN equals versus at that midpoint becomes the benchmark velocity for normalization. Soil-structure interaction for seismic assessment and design of bridges. Nonlinear behavior in supporting soil deposits rises with the increasing magnitude of the earthquake, allowing for more adaptability and dampening at the soil-to-foundation interface. It is still a difficult computational task to simulate the simultaneous development of inelastic mechanisms in the soil, foundation, and structure. This is because of both the material and epistemic uncertainty. To better understand how earthquakes interact with soil, foundation stiffness, and soil-foundation interfacial friction are all being studied. A hysteretic continuum of nonlinear weight and Poisson's ratio, G equals 18 knots per cubic meter, is supposed to be under the foundation of the building. At the surface, the soil's low strain shear modulus is 0, whereas, at 10 m below the surface, it is 213 MPa. Seed and Idris, 1970, advocated for SAM the fluctuations in shear moduli and damping ratios with shear strain. At a depth of 10 meters, the soft soil layer sits on top of a hard one. Using the Pile 3D finite element mesh, Wu and Finn, 1997, Finn et al., 2019, the soil deposit was split into 10 sublayers of varied thicknesses. Most design guides use the mean shear wave velocity versus to a depth of 30 m, versus 30, and the accompanying site classes to quantify the influence of the site on seismic design. Because of this, in most earthquake code standards, the top 30 meters of ground are used to characterize a site class. This single parameter, versus 30, determines the site's classification. In the ith layer, the shear wave velocity VSI is proportional to the height of the ith layer, which ranges from 0 to 30 meters. The characteristic period of soil TC, defined as the transition period between the constant acceleration and constant velocity segment of the elastic spectrum, is another attribute that distinguishes the various soil types by category. It's possible that soil's unpredictable and non-linear behavior could result in insufficient reliability. The variety of soil qualities can have a major impact on bridge behavior at the ultimate and serviceability limit states, which is why they must be taken into account. Please feel free to like, share and comment.